To start with, we have the filament circuit, and the filament circuit heats the filament when the machine is turned on. It heats the filament to incandescence, which is hot white, causing thermionic emission when the prep switch is depressed. You can think of incandescence like a light bulb. It rotates the disc when the prep switch is depressed. The secondary or high voltage circuit is the second part to the main circuit, and it includes the secondary coil of the high voltage transformer and all devices to which it is connected electrically. The wires have a smaller diameter than those in the primary circuit because they carry a lower current. The exposure switch activates the high voltage circuit, and the function is to produce an extremely high electrical pressure, which is the voltage, accelerating the space cloud and therefore producing X-rays. Now here's a picture of um, our circuit. I'm going to start off with the first part. So we have the very first portion is the primary circuit, and that's everything from number 1, which is from the electrical source, including the main breaker, the auto transformer with the line voltage compensator. It includes number 3, which is called a voltmeter. Oops. It includes the exposure switch, which is number 4. It includes the timer circuit, which is number 5. It includes number 6, which is the primary side of the high voltage transformer, which is a step-up transformer. Looking at this, this is the primary circuit, otherwise called low voltage. The second part that we have is the filament circuit. The filament circuit is going to continue down from the primary. It's going to include 3 parts, which is not much at all. It includes number 7, which is a MA selector. Part 8 is a filament ammeter, and part 9 is a step-down transformer, and we call it the filament transformer because it's in the filament circuit, and it heats the filament. That's its job. So we're going to write down that this is the filament circuit. And then we have the third part, which is the secondary side. So we're going to talk about 10, which is the secondary coil of the high voltage transformer. We're just going to close that gap there. It includes the number 11, which is the MA milliammeter, number 11. It has a ground wire, by the way. It has number 12, which are the rectifiers. And then it includes the cables coming down and going through the X-ray tube. Okay, and that is the secondary circuit. Now keep in mind that the primary is low voltage, the secondary is high voltage. The filament's low voltage as well, but the purpose of the filament circuit is to heat the filament. The purpose of the primary is to bring electrical voltage to the primary coil of the high voltage transformer. and the secondary is going to give us our high voltage and our low current so we can produce X-rays. So number one is the main breaker, and the circuit breaker or the fuses. It's called and also includes the on-off switch. We've got the line compensator and the auto transformer. We'll talk about each one of these in just a moment. The pre-reading kilovolt meter, which is a voltmeter. We have the exposure switch, which is going to allow X-rays to be emitted for a specific time. The first switch is called the prep stage, during which we have thermionic emission, which is boiling off of electrons. The anode rotates, and it prepares for the exposure factor selected. In the second switch, we have the exposure stage, and that's where electrons move from the cathode to the anode. We produce X-rays and infrared radiation. The timer circuit determines the length of the exposure. We have the synchronous timer, which was in fractions used for single phase units. The auto transformer is the most common, sophisticated, and complicated and accurate of the timers, and it's the one that's most commonly used, as I said. The mass timer has a combination of MA and time together, so it just has mass. And then there's the AEC timer, which we'll talk about AEC in a separate lesson, automatic exposure control. And then finally in the primary circuit, we have the primary coil, the high voltage transformer. The primary voltage is in voltage and the primary current is in amps. Both the primary and secondary coils are immersed in a special transformer oil for added insulation. Now in the filament circuit, we only have three parts. We have the MA selector, which is going to regulate filament current in amps to permit control of tube current, which is in milliamps. So filament current is in amps, which is very high current. When we have tube current, which is in milliamps, that's going to be very low. That's what's going to go across the X-ray tube. The filament ammeter measures filament circuit current, which is in amps. And the filament transformer decreases voltage and heats the filament because it increases current. Then we have the secondary coil, the high voltage transformer is the first part of the secondary circuit. It's going to switch from volts to kilovolts is what we end up having. And we're going to have milliamps as well. We're going to go from amps to milliamps. Notice that the amplitude of our wave increases as we increase our voltage. Then we have a milliammeter, which measures tube current, which is MA passing through the X-ray tube. And then we have rectifiers, which converts AC to pulsating DC. And last but not least, we have the X-ray tube, which is not part of either or any of the circuits. So looking at the individual parts that we just talked about, the first one is the main breaker, as we just talked about, and the on-off switch. It's going to include fuses or circuit breakers at the beginning of the whole thing. Number two is the auto transformer, which is going to select voltage, and it also has the line voltage compensator wired to it. Number three is the voltmeter, which is going to read what kilovoltage will be after we produce the X-rays. The timer, the exposure switch, which is number four, that's going to be the parts that's going to be taking the prep stage and the exposure parts to the exposure, taking the exposure. The timer circuit depends upon the type of timer you have, whether it's synchronous, electronic, mass, or AEC. And then number six is the primary coil of the high voltage transformer. So remember that you have two parts to a step-up transformer. We have a primary side and we have a secondary side. And the primary side is in the low voltage or primary circuit. Now on the other hand, we have the number seven, which is the MA selector. We have three types of MA selectors. This one happens to be a choke coil, but we also have two other types. There's also the rheostat, which is a resistor with a ability to change it. And then we also have the detachable reactor, which is the ability to have a DC, direct current, with a rheostat. Then we have the filament ammeter. The filament ammeter is going to measure filament current, which is going to be high current because we have low voltage right now. And then number 9 is a step-down transformer. It's going to increase current and decrease voltage. Remember that if we decrease the number of turns, we decrease voltage, we increase current, and that's going to heat the filament. And that's why it's connected to the filament. It's the very next thing it's going to be connected to. So it's going to heat the filament. The last part that we have is number 10, 11, and 12. Number 10 is the secondary coil, that high voltage transformer, where we're going to have kilovoltage and milliamps. And that's why at number 11 we have a milliammeter, because we're going to measure tube current, which is the current going across the X-ray tube, and that's going to be in milliamps. Number 12 are the rectifiers, which are we have 4 rectifiers. If we have 4 rectifiers, that means we have a full wave rectified unit. And then we have finally have the X-ray tube at the bottom. Notice that we have a voltmeter in this circuit. So if we have a voltmeter in the primary circuit, that is a parallel circuit. If we have an ammeter in the filament circuit, that means that it's a series circuit. And we have a milliammeter, which can be placed in different locations because it's a series circuit as well. So now we're going to talk about the 6 types of generators. The first type are the single phase. So single phase generators are either called single phase 1 pulse, which are half wave rectification, which means that we have 0, 1, or 2 rectifiers, and we're going to delete the negative pulses that we talked about in the last section. We're going to single phase 2 pulse machines have full wave rectification, which means we have 4 rectifiers. And that's exactly what we show here. We're looking at a full wave rectified unit, looking at where we inverted the negative pulse to positive. Okay, so we're going to take a look at how we go through the rectifiers, starting off with the negative side. This is going to be our positive pulse that we're going to start off with. We're going to start off from the negative side because electrons come from a negative side. We're going to go through A first because we're going to go opposite the arrow, not towards D. We're going to come down and we're going to produce X-rays. 1 X-ray, come back up. And now we have a choice of either going through C or D. The thing about C and D, about D, is that there's electrons that are going to repel each other. These two sets of electrons will repel each other. So instead of going through D, we're going to go through C. And we're to come down and we're finished with our process. Now at this point, we're going to switch to the negative pulse. And with the negative pulse, is where we left off was with the positive down here, now became negative. So this is negative and up here is positive. So to start off down here, and we're going to look at will we go towards C or we go towards B. And the reason why we go towards B, because we're going to go opposite the arrow. We're going to come down, we're going to produce X-rays. We're going to come back up. And we're going to see whether we're going to go towards C or D. Remember that the electrons are going to repel each other with letter C. Those two will repel. So we can't go towards C. So instead, we're going to go through D. And besides that, that positive charge is going to be attracting this. And that concludes our process of how our electrons travel through rectifiers. So three-phase power has 3 autotransformers. There's three-phase waveforms that are 180 degrees out of phase with each other. X-rays are produced continuously, And it's much more efficient process than what we had with single phase, because single phase X-rays were produced in bursts. So with single phase, we just had one phase of electricity where we converted that to, where we went through rectifiers, but now we're going to go through and we have 3 phases of electricity. So we're going to go through and they're 180 degrees away apart from each other. And we're going to produce, we're going to then rectify those negative pulses and get a total of 6 pulses going across in a positive direction. So the advantages of 3-phase generation of power is higher beam quantity, higher beam quality, which is nearly constant potential, very small ripple. We're going to have higher MA at very short exposure times, and the initial cost is going to be a big disadvantage. So with high frequency, we're going to talk about how we are going to have high full wave rectified power, where we have 2 positive pulses, and we're going to add that to batteries. And batteries only have current flowing in one direction as well. So when you put those 2 together, we end up with a really, really tiny ripple of less than 1%. So it's using batteries and silicone controlled rectifiers. It's much more efficient than 3-phase equipment. It's much smaller, less costly, and much more efficient. So taking a look at what we have ripple, which is going to change from 0 up to the kilovoltage that we have set. So this is 0, and that's why it's going to 100% change. Half wave and full wave both do that. Again, half wave is called single phase 1 pulse, and full wave is called single phase 2 pulse, but it's 100% change. Now, on the other hand, 3-phase 6 pulse doesn't start down here at 0. It's going to start up here, and so this number is actually 13%, but it's going to start at a little bit, it's not going to change very much. It's a 13% ripple. 3-phase 12 pulse is something we can do, is we can change the windings of the step-up transformer is all we have to do, and we get 4% ripple. And then high frequency has a ripple of less than 1%. Now, as far as abbreviations, we're looking at this phi symbol being used for the phase. So single phase 1 pulse for the half wave rectification. Single phase 2 pulse is the full wave rectification, which is a 1 phase 2. 3-phase 6 pulse is 3 phase 6. And then 3-phase 12 pulse is 3 phase 12. The number of rectifiers for single phase and high frequency are 1, and for the 3-phase we have 3 autotransformers. For the single phase 1 pulse, which is half wave rectification, we have 0, 1, or 2 rectifiers. For single phase 2 pulse, which is full wave, we have 4 rectifiers. 3-phase 6 pulse, we have 6 or 12 rectifiers, and we have 12 rectifiers with 3-phase 12 pulse. We have 60 pulses per second for single phase 1 pulse, 120 pulses per second for single phase 2 pulse, 360 for 3-phase 6 pulse, and 720 for 3-phase 12 pulse. And then the ripples are the same for the single phase units. They're both 100%. It's 13 to 14% for the 3-phase 6 pulse, and 3-phase 12 pulse is 4%. High frequency has a ripple of less than 1%. The capacitor discharge unit is depression of a charged button causes a rectification circuit to charge a capacitor. The signal indicates readiness when the capacitor fills to the appropriate level. Depression of the exposure switch triggers a discharge to the X-ray tube. The disadvantage is the capacitor may continue to discharge after usable exposure, which gives leakage of radiation. And so KVP limitations were an issue too. So portable units are a possible application. And so this is just showing that we have a set exposure KVP. We're ready for the exposure. We start the exposure and then we end it, but there's this period of time where the leakage is going to happen. This can be also used for chest units too, for their use for just chest X-rays only. The battery-operated mobile unit is based upon a nickel-cadmium battery supplied AC current. It supplies non-pulsating DC. Similar to three-phase 12 pulse, the advantages are exposure consistency, higher voltage, and no leakage possibility. The following load generator is a specifically designed three-phase or high-frequency generator in which the MA falls during the exposure. The function with MA unknown to the operator, so it is impossible to set the correct time. So it has to be used with AEC or mass timers are the only options. So exposures being in at the maximum, the MA drops, which is being falls as the anode heats, and it gives you the maximum use of tube limits. The purpose is to ensure the shortest exposure time.